All right, we're looking at our first example of continuous time convolution. So here's the problem. Given an LTI system with input x of t and impulse response h of t, find the output. And x of t is the unit step, and h of t is this decaying exponential. And I know it's decaying because we're given that a constant, is greater than 0, so the exponent is negative, meaning it decays. Now, before we get to mathematical details and so forth, let's understand what the problem is asking us to find. So we have a linear time-invariant system like this, and we're told that we're going to apply the unit step as a signal at the input, and we want to figure out what is the output. Okay, well, we need some sort of information about what's in the box other than it's linear and time invariant. So that information is that the impulse produces e to the negative at u of t. This is the impulse response. It is literally the response to an impulse. Okay, so given the impulse response, given that the system is linear and time invariant, and given the input, u of t, the output is simply the input convolved with the impulse response, and that convolution in continuous time is this integral here. All right, so let's do it. Now let's just do the math. So I'm going to take this perspective of tau being the independent variable. So let me plot x of tau. So I can do that very easily. Instead of just t, I'll replace the t's with tau. Okay, here's the origin. So the unit step is 0 here, and then it jumps to 1 there. Okay, there we go, and this goes on forever. And this is x of tau, right? Notice I've labeled the horizontal axis tau. Now, right underneath that, I'm going to sketch y, or excuse me, not y, h. And I'm going to sketch it relative to tau. Okay, but in h it appears as minus tau. So I'm going to take this signal, h of t, replace the t's with tau, and then flip it. So e to the negative at, that's a decaying exponential, and multiplying it by the unit step before you flip it means that we would have a decaying exponential in quadrant 1. However, after I flip it, that becomes a decaying exponential in quadrant 2. Or I guess you could say that that's an exponential increase now. And then because of the unit step, or the flipped unit step, we've got 0 in quadrant 1. Okay? And this goes on forever, and it never quite gets to 0. Right? That's the decaying exponential. So this is h of minus tau. And I've purposefully drawn one over the other like that, so they line up. Okay, now we're going to, so we've plotted versus tau, and we're going to shift by t. We're going to shift h, because that's where t occurs. T is a shift in h of minus tau. So notice that if we shift by anything less than 0, which means anything to the left. If we shift h of minus tau to the left, then there's no non-zero overlap. Imagine moving this plot to the left. This spike here, or all of this non-zero stuff, overlaps with the 0 stuff here. So when you multiply the two, you get 0. And then all of this 0 stuff overlaps with this non-zero stuff. When you multiply the two, you get 0. So again, if I shift by t less than 0, there's no non-zero overlap. So when you multiply x with h, you get 0, and when you integrate 0, you get 0. So that is all to say, if I shift by t less than 0, the output, y of t is equal to 0. Okay, that's part of our answer. Now, consider shifting by more than 0. And just, we'll put greater than or equal to 0, but it doesn't matter in continuous time. Now, imagine shifting this thing now to the right. If I shift by 1 second, or 1 unit of time, then my region of non-zero overlap is between 0 and 1. If I shift by 2, my region of non-zero overlap is between 0 and 2. In general, if I shift by t, the region of non-zero overlap starts at 0 and goes to t. Okay, so I'll write that down actually. Non-zero overlap between tau equals 0 and however much I shifted by, which is t. Okay, so for this region, for this range of t, the output, okay, is this integral, but I'm not going to integrate from minus infinity to infinity. I only need the non-zero part of this, because it's the non-zero area that contributes to the integral. So I'm going to integrate my bounds, right? This is with respect to tau, and so tau goes from 0 to t. Like that. Now, x of tau, well, in the non-zero part, x is just 1. So I'm just not even going to write it. There's a 1 there. And in the non-zero part, we're talking about this part of h, right? So that's e to the negative at, but h of t minus tau, that's e to the negative a, and then if this is h of t, when h of t minus tau is replacing t minus tau with t. So I think I said that backwards, replacing t with t minus tau. Like this. And I don't need the unit step because the unit step is 1 in the non-zero part, the non-zero region. Okay, so now my convolution boils down to just summing finding this integral. Okay, so I can use property of exponents. I can pull out an e to the negative at because I'm integrating with tau, so t is a constant. So I'll bring that out. E to the negative at, integral from 0 to t of e to the a tau, d tau, like this. Okay, that integral is easy to do. This is negative e to the negative at. Then the integral of e to the a tau d tau, there's a 1 over a that comes out. E to the a tau integrated from 0 to t. So I plug in t for tau, and I get 1 over a e to the negative at times e to the at, right? That's what I get when I plug in tau for t. And then when I plug in 0, e to the 0 is 1. Okay, now if I distribute e to the negative at in, I get 1 over a, and I get 1 minus e to the negative at. That's the other part of our answer. So for this range of t, this is our answer. So we can combine those two parts using the unit step. We can say that, well, let me back up. We can write a piecewise function. We can say that the total output is this 1 over a, 1 minus e to the negative at, when t is greater than or equal to 0, 0 else. Or I can use the unit step to write this more compactly and say that the output is 1 over a times 1 minus e to the negative at times the unit step. Either one is fine. This one is probably preferred. Okay, that's it. Let's draw it. Let's see what it looks like if we were to draw that. Just sketch it quickly. Notice how it's a function of t, not tau, right? Because when you plug in bounds for tau, the taus go away. Okay, so because of the unit step, we've got 0 here. And then as t goes to infinity, e to the negative at goes to 0. So we're subtracting something less and less from 1, or 1 over a. So this asymptotically approaches 1 over a, like that. Okay, finally, now that's the answer. Now finally, I want to make some sense of this answer, and I want to give you a physical situation where you would see this. Now, I'm going to erase a little bit. Okay, erase a little bit. In circuits class, basic circuits, and don't worry about it. If you don't remember circuits, that's okay. But you should have seen something like this. If you had 1 volt here, and you had some sort of switch, where you switch this in at t equals 0. And you had a resistor and a capacitor, right? And you looked at the voltage across the capacitor. Okay, I'm sure you solved a problem like this. Okay, so first of all, notice that before you switch, you have 0 volts applied. And then right after you switch, you've got 1 volt applied. And that happens at t equals 0. So that's exactly x, right? Because the unit step is 0, and then at t equals 0, it becomes 1. So this is the unit step. So if we're considering, the switch and the 1 volt to be the input, that's the unit step. Now, we're looking at the voltage across the capacitor, that's the output. And actually, we can show, and later on in the course we will show, that the impulse response to this circuit, here's our circuit, in red, the impulse response is exactly this. That's the impulse response to an RC circuit. And A is related to the time constant, R times C. Okay, so this is basically saying when you switch in that voltage, what's the voltage across the capacitor? You solved this problem in circuits class. The answer was this. And you even gave the equation, this, that the capacitor charges up when you switch that 1 volt in. It charges up. And that's exactly what we just found. However, we did not use circuit analysis. We used, of course, signals and systems. Again, don't worry too much if you don't remember circuit analysis. That's okay. We won't use circuit analysis in this course.